Welcome back to the Deep Dive. Today we are on a critical mission. We're giving you the ultimate shortcut to mastering the core chemistry for the Cambridge AS and A level.
And this is a tricky section.
It is. We're diving into material that forces you to constantly switch gears. And we're here to make that switch feel seamless.
That's absolutely right. I mean, the challenge is the intellectual whiplash. We're covering two different worlds.
Totally.
On one side, you have P1, the practical skills. It's all about minimizing uncertainty, getting precise data at the lab bench.
And then the other side.
Chapter 19, pure thermochemistry, all about calculating and understanding energetic stability with things like Hess's law. Success here really demands you master both, the hands-on work and the heavy math.
Okay, let's unpack this then. We need a thread to hold these two worlds together. So we're going to frame this deep dive around two concepts: uncertainty in the lab and balance in the theory.
I like that.
We'll start by making sure every experiment you run is solid. And then we'll leap into those, dramatic energy calculations for building and breaking ionic lattices.
All right, let's do it. All good science, all good investigation, it starts with structure.
Right.
We're trying to find out how one thing affects another. A classic example is investigating how concentration affects reaction rate, like mixing sodium thiosulfate and hydrochloric acid.
Oh, the one that makes that cloudy sulfur precipitate.
That's the one. And if you can't define your variables from the get-go, you haven't really done science.
So three types. First, the one you're actively changing. That's the independent variable.
Yeah. In this case, the acid concentration.
Then you've got the dependent variable. That's the result you measure, right? The effect of your change.
Exactly. Here, it's how long it takes for the solution to get so cloudy you can't see through it.
Yeah. And finally, the things you have to keep the same for a fair test. These are the control variables.
Non-negotiable.
Yeah, so that's making sure every trial is at the same temperature, same total volume, maybe even the same little X on the paper underneath the flask.
That structural thinking then leads right into how you show your results. So we've got the variables sorted, but what about the graph? That's a common place to trip up.
There's a golden rule, and it's all about the independent variable.
Okay.
If your independent variable is continuous, so it can be any numerical value in a range, like temperature or time, you have to draw a line graph.
But if it's categoric, so it's described with words like different types of metal or different salts, then it's a bar chart.
And getting that right is crucial. But before we get any further, I want to pause on some of that jargon. We hear accurate and precise all the time. Can you just, nail that difference for us with a simple analogy?
Absolutely. Think of a dartboard. Precise results are like all your darts landing in a tight little cluster, but way off in the bottom corner.
So they're consistent, but consistently wrong.
Exactly. Accurate results are centered around the bullseye. They reflect the true value. Ideally, of course, you want both.
Right. A tight cluster right on the bullseye.
That's the goal. Now let's quickly define the other key terms. Range is just the minimum and maximum values you test.
So like from 0.2 up to 1.0 molar.
Yep. The interval is the step between those values. So maybe you go up in steps of 0.2. And an anomalous result, that's just a data point that clearly doesn't fit the pattern, the odd one out.
Okay, so moving into the actual execution, the quality of your observation is huge.
It's paramount. And let's clear up a classic confusion, the terminology. If a liquid is transparent with no color at all, the word is colorless.
Now, not clear.
Right, because clear just means transparent. It could still be blue, like copper sulfate solution. You have to be specific.
And for something technical, like a titration, what's the standard?
The standard is concordant titers. You repeat the experiment until you have two results that are within 0.1 cubic centimeters of each other.
And that first one is usually just a rough go.
Right. Yeah, the first titer is usually just to find the ballpark. You never include it in your final average.
Okay, let's talk about actually reading the measurements. The burette, for example.
Yes. Precision on an analog scale. So say the scale has divisions every 0.10 meters cubed. The rule is you must read it to within half the value of those fine line divisions.
So 0.1 euro divided by 2. You have to record to the nearest 0.05.
Right.
Like 15.35.
Exactly. If you just write 15.3 or 15.4, you lose the precision marks instantly.
And that precision has to carry through to your data presentation. The table.
Draw it before you start. Independent variable in the first column, dependent in the second. And the column headings, this is so important, must have both the quantity and the unit. No exceptions.
Graphing has its own strict rules, too.
Of course. Independent on the x-axis, dependent on the axis. Use sensible scales. Think increments of 1, 2, 5, or 10 per square. Not weird numbers like 3 or 7.
And please, No dot to dot.
No, never. You draw a single, smooth line of best fit.
Okay, finally, calculations. Significant figures. This is where it all comes together.
This is the weakest link principle. Your final answer can only be as precise as your least accurate piece of data.
Can you give an example?
Sure. Let's say a reactant concentration was given to you as 0.200 moles per decimeter cubed. That's 3 significant figures.
Right.
Even if you measure your titer volume to 4 sig figs, like 15.35, your final calculated answer must be rounded to 3 significant figures, because that initial concentration is your weakest link.
That makes sense. The final result can't be more certain than its least certain component.
Precisely. So once the data is plotted, interpretation is about describing the patterns. And if you need the gradient from a straight line,
Which usually represents a rate or a constant of some kind.
it does. You have to choose 2 points on the line that are far apart, at least half the length of the line. This minimizes your percentage error.
Okay, this brings up a good question. We've talked about precision, but what are the things that actually challenge our results? The types of errors.
Right. 2 main types. First, random errors. These are things that scatter your results, a little too high or a little too low. Human reaction time misreading the scale slightly.
And you fix those just by repeating the experiment and taking an average.
Exactly. But the second type, systematic errors, are more dangerous.
Why is that?
Because they push all your results in the same direction, like a balance that wasn't zeroed properly, or always reading the top of the meniscus. Repeating the test won't fix that.
You have to actually change your method or your equipment.
You do, and we can quantify the damage from these errors using percentage error. It's the error in the reading divided by the actual reading times 100.
And here's a really useful tip, especially for calorimetry. When you measure a temperature difference.
The change in temperature, delta T.
Right. You have to add the error margins from both the start and end readings. So if your thermometer is accurate to, say, plus or minus 0.5 degrees,
then the total error in your temperature change is 1 degree. 0.5 plus 0.5 error.
which leads to a really key insight. If you measure a small temperature change like 5 degrees, that 1 degree error is huge. It's a 20% error.
But if you measure a big change, say 92.5 degrees, that same 1 degree error is tiny. It's just over 1%. So measuring a larger change makes you more certain.
And that links perfectly to what we're about to do. But before we leave the lab, a final thought. Your conclusions can only ever support a hypothesis. You can never claim to have proven it.
Because you're limited by the range of your experiment.
Exactly. And to improve accuracy, you need to suggest specific changes, not just use a better thermometer, but something like replace subjective observation with a light meter.
Okay, so let's make that shift. We're moving from minimizing physical uncertainty to calculating energetic certainty. And that starts with the big one, lattice energy.
Delta H lat.
Right. The definition is key. It's the enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions under standard conditions.
Gaseous ions is the critical phrase there. And because you're forming strong bonds in the lattice, energy is always released. So lattice energy is always exothermic.
Always a negative value. And since you can't measure it directly, you have to calculate it with a Born-Haber cycle.
Which needs a few other steps. First up is enthalpy of atomization.
Delta H at. This is the energy needed to form 1 mole of gaseous atoms from an element in its standard state. You're breaking bonds, so always costs energy, always positive.
Then you need to form the ions. For the nonmetal, that's first electron affinity, EA1.
This is adding 1 mole of electrons to 1 mole of gaseous atoms. For something like chlorine, this is favorable. It releases energy, so it's usually exothermic or negative.
And this is a big, but successive electron affinities are different.
Very different. The second or third electron affinity is always endothermic, always positive.
Why is that?
Think about adding an electron to an already negative ion, like O- becoming O2-. There's massive electrostatic repulsion. You have to pump energy in to force that second electron on.
And that repulsion explains some weird trends, right? Like with fluorine.
Exactly. Electron affinity generally gets less exothermic down a group, but fluorine is an exception. Its EA is less negative than chlorine's. The fluorine atom is just so small, its existing electrons create so much repulsion that the incoming electron isn't as welcome.
Okay, so let's bring all these pieces together in the Born-Haber cycle.
It's just Hess's law, really.
Yeah.
You're comparing 2 paths to the same product. The direct path is the enthalpy of formation, delta HF.
And the indirect path is all those steps we just defined. Atomization, ionization, electron affinity, and then finally, forming the lattice.
So the equation is basically Delta H formation equals the sum of all the intermediate steps plus the lattice energy. You just rearrange it to solve for the lattice energy.
And what's the number one mistake people make here?
Forgetting the stoichiometry. If you're making MgCl2, you need to remember you're using 2 moles of chlorine atoms.
So you have to double the atomization energy and double the electron affinity for chlorine.
You do. It's an easy mark to lose.
So what actually controls how big the lattice energy is?
It really comes down to 2 things: charge and size. Ionic charge is the biggest factor by far. If you double the charges, like going from LiF to MgO,
That's +1 and -1 versus +2 and -2.
the lattice energy becomes hugely more exothermic. It goes from about -1,000 to almost -4,000.
Yeah. And the other factor is size.
Ionic size. The larger the ions, the more spread out the charges. Weaker forces, so a less exothermic lattice energy.
And this idea of charge being concentrated in a small space, that leads to ion polarization.
Yes. This is where a small, highly charged inclination distorts the electron cloud of a large anion.
And that has real-world consequences, right? Like for thermal stability.
It does. Think about group 2 carbonates. Their stability increases as you go down the group.
So magnesium carbonate is the least stable, barium carbonate is the most stable.
Exactly. Because the tiny Mg2 plus ion at the top is a powerful polarizer. It distorts the large carbonate ion, weakens its internal CO bonds, and makes it decompose more easily.
Whereas the big B2 plus ion at the bottom doesn't polarize it as much, so it's more stable.
That's the logic.
Okay, let's wrap up with the energetics of dissolving things. The enthalpy of solution.
Delta H sol. The energy change when 1 mole of an ionic solid dissolves. It can be endo or exo. If it's a small positive or small negative number, the salt is probably soluble.
And you can measure that in the lab with a simple calorimetry experiment. Measure the temperature change, then use Q equals mc delta T.
Exactly. The energy transferred is minus mc delta T. That gives you the experimental value.
But dissolving is a 2-step process in theory. You break the lattice, then you hydrate the ions. And that second part is the enthalpy of hydration.
Delta H hyd. That's the energy released when 1 mole of gaseous ions dissolves in water. You're forming new bonds between the ions and the water molecules.
And since you're forming bonds, it's always exothermic, always negative.
Yes. And just like lattice energy, it's more exothermic for smaller ions with higher charges. That hydration energy is what pays the price for breaking the lattice apart.
So we can connect all 3, lattice, hydration, and solution, with another energy cycle.
Another application of Hess's law. Basically, the energy to break the lattice plus the energy change of solution equals the energy you get back from hydrating the ions.
And this cycle explains that really complex trend for group 2 sulfate solubility.
It does. Solubility decreases dramatically down the group. MgSO4 is soluble, BaseO4 is famously insoluble.
So why is that? As we go down the group, the cation gets bigger.
Which means the enthalpy of hydration becomes less exothermic. It decreases rapidly because it's very sensitive to cation size.
At the same time, the lattice energy also gets less exothermic because the ions are bigger.
But, and this is the key, it decreases slowly. Because the huge sulfate anion is so big, it sort of masks the change in the cation size.
So the energy you get back from hydration drops off a cliff, but the energy you need to break the lattice only goes down a little bit.
Exactly. The net result, the delta H of solution, becomes more and more positive, more endothermic, so the substance gets less and less soluble.
So what does this all mean then? We started with practical uncertainty, how to measure things to the nearest 0.05. And we ended up explaining these huge macroscopic trends.
It's all connected. The simple question of whether a salt dissolves or whether it decomposes, it all comes down to this delicate, energetic tug of war.
A balance between the energy needed to break the lattice apart and the energy gained from hydrating the ions.
That's it. Understanding that balance, which is informed by precise data from the lab, that's the core theme that runs through all of this. It's chemistry playing an energetic tug of war.
We really hope this knowledge helps you feel ready to tackle those complex calculations and ace those practical components. Thank you for joining us for this deep dive.